Dear students, welcome to the lecture series on the topic Engineering Graphics. Today we are going to discuss about projections of the solids. I am Dr. IPS Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. Now here we have been provided with a triangular pyramid which is having edge of the base equal to 35 millimeter and axis height it is equal to 65 millimeter. And since we have been provided with edge of the base 35 millimeter, so it means that this triangular pyramid it is having base as equilateral triangle, and this triangular pyramid it is resting on a side of its base on the horizontal plane, while the axis of the pyramid it is inclined at an angle of 45 degree with respect to the horizontal plane, and the true length of the axis it is inclined at an angle of 35 degree with respect to the vertical plane. So we are required to draw the orthographic projections of this oblique triangular pyramid. So let us first of all evaluate the orientation of this triangular pyramid as it is resting on the base on the horizontal plane. Now here if we are going to take this orientation as the location of the base onto the horizontal plane, now we will find that while we incline the axis of this triangular pyramid with respect to the horizontal plane, either it will be resting on this corner or it will be resting onto this corner if we incline it this way. So no way this triangular pyramid will be resting on the horizontal plane on the edge of the base over here. So if we assume that we are going to take the orientation of the triangular pyramid into this position, now we can see that if we incline this triangular pyramid with respect to the horizontal plane in this orientation, then we will find that this triangular pyramid will be resting on the horizontal plane on one of the edges of its base over here. So this way, this is the correct orientation of the triangular pyramid, as we are going to look at this triangular pyramid from the top side. So here this is the apex of the triangular pyramid, A, B and C. So these are three corners of the base and these are the three edges AB, BC and CA over here. So as we incline the axis of this particular triangular pyramid at an angle of 45 degree with respect to the horizontal plane, so as we incline it this way, now we will find that this triangular pyramid will be resting on the base in the horizontal plane on one of its sides over here, which happens to be HBC over here. So this way we have to start with the construction of the orthographic projections of this particular triangular pyramid. First of all, we are going to look at the solid from the top view. So the top view of this triangular pyramid will be an equilateral triangle having h is equal to 35 millimeter. While in the front view, we are going to observe the triangular projections of this pyramid into the front view projections. So let us proceed with the construction of the orthographic projections of this oblique solid. So to begin with, we assume that this triangular pyramid it is resting on its base in the horizontal plane into this orientation such that HBC happens to be perpendicular to the vertical plane. So let us first of all draw the top view projections of this triangular pyramid. So here we have got an equilateral triangle having h is equal to 35 millimeter. Now A, B and C represents the top view projection of this triangular pyramid. Now here we can see we have got this point as the apex. So here we will be having point O located over here. So OA, OB and OC, these are the three slant edges which will also be visible to us as we look at this particular triangular pyramid from the top. So in order to locate this apex point, what we have to do? So from point A, we are going to draw a perpendicular bisector of the edge BC. Similarly, from point B, we are going to draw a vertical projector of the edge AC. And finally, from point C, we are going to draw the vertical projector of the edge AB. So wherever these three perpendicular bisectors drawn from the three corners of this particular equilateral triangle, they are going to intersect. So this point will be providing us with the location of the axis of this particular triangular pyramid. So this way, this apex point or the axis OO1 will be located over here. Now having located this apex point or the axis point OO1, now we can join OA, we can join OB and we can join the third slant edge OC over here. So the three slant edges OA, OB and OC, they have been joined as they are visible to us from the top view projections over here. So OA, OB and OC, they have been joined in the top view projections. Now having completed the top view projections of this triangular pyramid, now let us proceed with the construction of the front view projections of this triangular pyramid. So we know that this is the axis point. So here we have drawn the axis from the point OO1. So O point, it is the apex point, while O1 point, it is the axis point which is available with us onto the base of this triangular pyramid. So here we know that this height of OO1 in the front view, this is provided to us as 65 millimeter. So now we are going to mark this axis height is equal to 65 millimeter. The moment we mark this axis height, the apex point O dash has been located in the front view projections over here. So now we can see that point A, it will be projected onto the XY reference line over here as A dash. Similarly, points B and C, they will be projected onto the XY reference line, that is the base of this triangular pyramid, as B dash and C dash over here. And finally, this point O1 is there, which it is lying on the bottom of the axis onto the front view projections over here. So this way, all the 5 points, they have been appropriately marked and located into the front view projections. Now we can join the slant edge O dash A dash. We can join slant edges O dash B dash and O dash C dash over here. Now we know that the slant edges O dash C dash and O dash B dash, they have overlapped with each other in the front view projections over here. Now one thing we must remember over here, that this slant edge OC, it is lying on the rear side of the solid. So as we are going to look from this side, OC slant edge, since it is lying on the rear side of the solid, it will be appearing as a dotted or a hidden line projection, that is O dash C dash in the front view projection. Whereas the slant edge OB, since it is visible to the observer, this will be appearing as a solid edge or a solid line projection as O dash B dash in the front view projection over here. So since this object line projection O dash B dash corresponding to this slant edge OB, it is going to supersede the hidden line projection, that is O dash C dash over here in the front view projections. So we are not able to see this hidden line projection corresponding to the slant edge O dash C dash in the front view projection. So we are going to get the object line projection corresponding to O dash B dash superseding or overlapping the hidden line projections corresponding to the slant edge O dash C dash over here. So now we can also join the projection corresponding to A dash and B dash C dash over here. So this way the base projection we have also joined. So now we have been able to obtain the front view projections corresponding to this triangular pyramid which is resting on its base into the horizontal plane. Now we have been provided with the information that in this triangular pyramid, the axis of the pyramid, it happens to be inclined at an angle of 45 degree with respect to the horizontal plane. So now over here we have to tilt this particular triangular pyramid in such a way that this axis, that is O dash O1 dash, it should be inclined at an angle of 45 degree with respect to the XY reference line. So now if the axis of the solid is inclined at an angle of 45 degree with respect to the horizontal plane, so the base of this particular triangular pyramid, it will be inclined at an angle of 90 degree minus 45 degree with respect to the horizontal plane. That is, we have to shift or transform this front view projections which we have obtained previously in such a way that the base of this triangular pyramid should be inclined at an angle of 45 degrees. So automatically the axis of this triangular pyramid will be inclined at an angle of 45 degree with respect to the horizontal plane. So now we have to rotate this triangular front view projection which we have already obtained over here in such a way that we have to locate or orient the base over here at an angle of 45 degree. So this angle of inclination of the base with respect to the horizontal plane, this orientation is 45 degree. And now if this angle of orientation of the base is 45 degree, now we have to locate these 3 points. So B dash, C dash will be located over here as B1 dash, C1 dash over here. Now we will be measuring this distance between B dash, C dash and O1 dash. So point O2 dash will be located over here at the same distance. Similarly, the distance between O1 dash and A dash will be measured from this front view projection, and now this distance will be marked alongside the orientation of the base. Now we can see we have marked point 1, point 2 and point 3 over here corresponding to the base of this particular triangular pyramid as it appears to us in the front view projections which we had already drawn. So distance of B dash, C dash and O1 dash, this we have marked over here. Similarly, the distance of O1 dash and A dash we have marked over here, and we also know that the distance between O1 dash and O dash, that is the axis height, this is also equal to 65 millimeter. So this axis height we have marked as 65 millimeter. So point 1, point 2, point 3 and point 4. So all these 4 points, they have been appropriately located such that the triangular pyramid, it will be resting on one of the sides of the base onto the horizontal plane, while the axis of this triangular pyramid happens to be inclined with respect to the horizontal plane at an angle of 45 degree. Now we can see that this orientation of the axis, it is 45 degree with respect to the horizontal plane. So now having obtained the rotated view or the transformed view corresponding to this inclined triangular pyramid in the front view projections. Now, the corresponding top view projections of this inclined triangular pyramid needs to be obtained. So how we can obtain the top view projections? Now we can observe that into the front view we have got 5 points over there, A1 dash, B1 dash, C1 dash corresponding to the base, and O1 dash and O11 dash, it is corresponding to the axis. So total of 5 points they are available with us in the front view projections. Now from these 5 points we are going to draw the vertical projector lines as we are going to look at this particular inclined triangular pyramid from the top view. So now once we draw these 4 vertical projector lines emerging from these 5 points of the front view elevation projection, now we are going to now construct the horizontal projector lines from the 5 points of the plan projection view which we had obtained earlier, and wherever the horizontal projector lines drawn through these 5 points of the plan projection view, they are going to intersect with the corresponding vertical projector lines which are emerging from the front view projections. So we are going to get these points of intersection as the corresponding plan projection points corresponding to this particular inclined triangular pyramid. So let us start with point C. So from point C we are going to draw a horizontal projector line. So wherever this horizontal projector line drawn through point C, it intersects with the vertical projector line drawn from the point C1 dash, we obtain the point C1 in the top view projection. Similarly, here we have got 3 points alongside this projection line. So here we can see second projector line we have drawn over here. Now onto this second projector horizontal line, we have got 3 points which are lying over here. Point A, point O and point O1. Now let us find out the corresponding points of intersections with the vertical projector line. So the horizontal projector through A, it intersects with vertical projector through A1 dash at this position. So we obtain the point A1 over here. Similarly, horizontal projector drawn through point O, it intersects at this position with the vertical projector drawn through the point O1 dash of the elevation. So we obtain the point O1 over here. Similarly, the horizontal projector line drawn through the point O1, it intersects here with the vertical projector line drawn through the point O11 dash. So wherever this intersection happens, we have been able to obtain point O1 over here. And finally, here we have the point B corresponding to the plan projection view. Now from this point, we are going to draw another horizontal projector line and extend it up to the limit where it is going to intersect with the vertical projector line drawn through the point B1 dash of the elevation. So this way, all the 5 points of the plan projection view, they have been obtained. Now which points we have to join? We need to join A1, B1 and C1. We also need to join O with A1. We need to join O with B1. We also need to join O with C1 over here. And besides this, we will also be joining O1 and O11 as the plan of the axis over here. Now, which edges they need to be joined using object line and which edges they need to be joined using the dotted or the hidden lines over there. So now you can check as we are going to look at this particular inclined solid from the top. So points B1 dash and C1 dash points, they are located farthest away from the observer. So observer is located over here. Now B1 dash and C1 dash points, they are located at the farthest distance away from the observer. So all the edges or the lines which are going to join B1 and C1 in the top view, they will be drawn dotted unless those edges they appear as the boundary of the object. So let us join these points, A1 with B1, B1 with C1 and C1 with A1. So here we can see all edges joining B1 and C1, they should have been drawn dotted, but A1 B1 it is lying onto the boundary, so this has to be drawn dark. Similarly, A1 C1 it is also appearing on the boundary of the object, so again this has to be drawn dark over here, that is using the object line. But B1 C1 we have to draw as the dotted line or the hidden edge over here. Similarly, as I told you earlier, we need to join O1 with A1, O1 with B1 and O1 with C1 also. So now O1 A1 has been joined, O1 B1 has been joined and O1 C1 has been joined. Now again we can see any edge joined with B1 and C1 should have been drawn dotted. But again O1 B1, since this edge is falling onto the boundary, so this has to be drawn dark. Similarly, O1 C1 is also lying onto the boundary of the solid. So again, this will not be drawn dotted, rather this will be drawn dark. So this way, we have been able to obtain the plan projection corresponding to this inclined triangular pyramid when the axis of the pyramid it is inclined at an angle of 45 degree with respect to the horizontal plane. And now into this plan projection, one thing is very much evident, that this axis O1 O11, so this is the apparent length projection of the axis as it appears to us into the top view projections over here. Why? Because the axis O1 dash O11 dash it happens to be inclined at an angle of 45 degree with respect to the horizontal plane. So the top view projection of this particular axis as it appears over here in the top view projections, this will be the apparent length projection of this axis over there. But in the problem statement we have been provided with this information that the angle phi means angle of inclination of the true length of the axis with the vertical plane happens to be 35 degree. So here angle phi is available with us, which is the angle of inclination of the true length of the axis with respect to the vertical plane. But here in the top view projections, what is available with us? It is the apparent length projection available over here. So now since the axis length O1, O11 as it appears to us in the top view projection over here, it is the apparent length. So here angle beta needs to be evaluated over here. So how do we evaluate angle beta? When angle phi is given to us. So here what we have to do is we have to draw the angle phi over here. So angle phi is equal to 35 degree. So from this point we have drawn a projection line or a construction line which is inclined with respect to vertical plane at an angle of 35 degree. So since this is angle phi, now alongside this construction line or the projection line, we have to mark this distance which is equal to O1 dash, O11 dash, which is equal to 65 millimeter. So this is the true length of the axis, because angle phi is the angle of inclination of the true length of the axis with the vertical plane. So here this is the length equal to 65 millimeter. So alongside this orientation projection line, we have to mark 2 points appropriately over here in such a way that the distance between these two axis points, it happens to be 65 millimeter, which is equal to true length of the axis. So having marked these 2 points, So we have labeled these 2 points as O21 corresponding to this point or this point, that is the axis point, and O22, that is point of the axis on the base of this triangular pyramid. So having located these 2 points over here, now we have to draw 2 projection lines over here parallel to the XY reference line. And now from the principle of rotation of the line, we know that whenever we have got these 2 construction lines drawn over here, one through O21, another construction line we have drawn through O22. So between these 2 locus lines or the construction lines, the true length of the axis will be lying, as well as the apparent length of the axis, it will also be lying between these 2 locus lines over here. So this is the basic fundamental of the principle of rotation of the line. So here from point O11, now we are going to measure this length or the apparent length over here. So this is the apparent length of the axis now which we need to measure. Distance between O1 and O11. So now with this as center, with O22 as center, we have measured this distance. Now we'll mark one arc is equal to the apparent length of the axis. Why we have to mark this apparent length? Because ultimately we are required to transfer top view projection from position number 4 to position number 5 over here. So now we have already marked the true length over here at an angle of phi is equal to 35 degree. We have measured the apparent length of the axis. Now this length we are going to mark between these 2 locus lines. So now once we mark an arc over here, now we can join O22 with O2. So this point will be labeled as O2. So this point is O2. This point is O22. So this length, it is equal to apparent length and it is equal to O11 distance over here. So having marked this apparent length, now we know that this is the orientation along which this figure of plan projection needs to be rotated over here. So now having located this orientation of the axis, that is the apparent length of the axis, now we are going to measure this angle of inclination of the apparent length of the axis with respect to the vertical plane. And this angle of inclination is called angle beta. And we know that apparent angle of inclination, it is always greater than the true angle of inclination. So angle beta happens to be greater than angle phi. So now we have to reorient this top view projection over here. So now in order to rotate this top view projection, this orientation line has been obtained. Now we are going to extend this orientation line over here so that it intersects with the XY reference line. So this angle happens to be 42 degree over here. So now with respect to this orientation line, that is O22, now this figure which we had obtained earlier, that is the plan projection, needs to be reoriented. Now once again we are going to mark all these points over here into this plan projection view. So how we can do that? We have to locate the location of all the 5 points which we had got into the plan projection view. So how we can do it? Please check. This is point O22. This is point O2. So this is corresponding to O11 and O1. So now we know that we need to measure this distance. So from O1, as we move towards O1, we measure this distance. We'll put a dot over here. This is corresponding to the orientation of the points B1 and C1. So once we measure this distance, please check. We have measured this distance and marked it over here. And once we obtain this point, now we know that from this point, as we move in the perpendicular direction by this distance, point B1 will be located. As we move perpendicular to this axis line. By this distance, point C1 will be located. So we have measured this distance of this point from O11, and then we have drawn a construction line. We move this distance, point B1 will be located. We move this distance, point C1 will be located. We can check B1 along this side and C1 along this side will be located. Similarly, from O1, we measure this distance along the axis orientation, point A1 will be located. And as we move along this side, point O2 or O1 will be located over here. So please check from O2, if we draw this point, so point A2 will be located over here. This distance, it is equal to this distance, and again point 1, 2, 3, 4, 5. All the 5 points, they have been located over here using rectilinear distances. So we have used the principle of rectilinear distances to locate all of these 5 points. So now having located these 5 points, point 1, 2, 3, 4 and 5. Now we can transfer this plan projection from this orientation to this orientation. So what does this change in orientation means? We can check that the plan of the axis over here, this will be inclined at an angle of 42 degree with respect to the vertical plane. So it means that the true length of the axis is inclined at an angle of 35 degree, while the plan of the axis will be inclined with respect to vertical plane at an angle of 42 degree. So now having identified these 5 points, now we have marked these 5 points onto the plan projection view. Now we have got the plan projection corresponding to this oblique solid in which the axis was inclined at an angle of 45 degree with respect to the horizontal plane, and the true length of the axis, it is inclined at an angle of 35 degree with respect to the vertical plane, or the apparent length of the axis, it is inclined at an angle of 42 degree angle beta with respect to the vertical plane. So having obtained the plan projections, now the corresponding front view projections of this oblique solid needs to be obtained. So how the corresponding projections of the elevation can be obtained? So once again, as we are going to look at the solid from this orientation, we had 1, 2, 3, 4 and 5 points available with us. So from these 5 points, what we can do? We can draw the vertical projectors in the upward direction, and we need to find out the corresponding points of intersections of these vertical projector lines with the corresponding horizontal projectors, which will be emerging from the corresponding 5 points of the previous elevation projection view. So now let us start evaluating the elevation projections corresponding to the oblique triangular pyramid. So here we have got point O1 dash. So from O1 dash we have drawn a horizontal projector line. So wherever this horizontal projector line, it is going to intersect with the vertical projector drawn through O2, we are going to obtain the location of the point O2 dash, that is the apex point corresponding to this oblique solid. Next, we have got point A1 dash in the elevation. From point A1 dash in the elevation, we have drawn a horizontal projector line. Wherever it intersects with the vertical projector drawn through the point A2, this point of intersection provides us with the location of the point A2 dash in the front view. Next, we have got points B1 dash and C1 dash in the front view located onto the XY reference line. Why? Because this solid is resting onto the edge of the base on the horizontal plane. So B1 dash and C1 dash points, they are available onto the horizontal plane, that is onto the XY reference line. So as we draw a construction line from B1 dash, so we will find that this horizontal construction line from B1 dash, wherever it intersects with the vertical projector line drawn through the point B2, this intersection point provides us with the location of point B2 dash. Similarly, here we have got vertical projector through C2 intersecting with horizontal projector drawn through the point C1 dash. So this point of intersection provides us with the location of the point C2 dash. And finally, here we have got point O22. So the vertical projector drawn through O22, it intersects with the horizontal projector drawn through the point O11 dash. So the fifth point in the elevation that has also been located. Now, as we are looking from this side, so point A2 is the point which is farthest away from the observer. So any edge or any line which is going to join with A2 dash in the front view should be drawn as a dotted line unless that edge or that line appears to be available with us in the boundary of the solid. So rest everything will be drawn dotted. Now which are the points or the edges which we want to join? A2 dash, B2 dash and C2 dash need to be joined. O2 dash, A2 dash, O2 dash, B2 dash, O2 dash, C2 dash need to be joined. So let us join the points in the elevation. We can see A2 dash and B2 dash, because it is lying in the boundary, it will be drawn solid. It will not be drawn dotted. B2 dash, C2 dash, it is visible to the observer. So this again has to be drawn solid or using the object line. So this edge A2 dash, C2 dash, because it is lying on the back side, so this will be drawn dotted or the hidden line over here. Now we can join A2 dash with O2 dash, but again because it is lying in the boundary, it has to be drawn using the object line. Now O2 dash, B2 dash needs to be joined, O2 dash, C2 dash needs to be joined. So this way we have been able to join all the edges in the front view projection corresponding to this oblique solid. And finally, O2 dash and O21 dash, this is the axis over here. So this axis also needs to be joined using a center line over here. So axis line has also been joined, whereas all other edges, they have also been joined over here. So this way we have been able to obtain the front view projections as well as the top view projections corresponding to this oblique solid, in which the axis is inclined at an angle of 45 degrees with respect to the horizontal plane, and the true length of the axis, it is inclined at an angle phi is equal to 35 degrees with respect to the vertical plane. So with this we complete the discussion of construction of orthographic projections of the oblique triangular pyramid, in which axis of the pyramid, it happens to be inclined with respect to horizontal plane as well as the vertical plane. So this is all for today. So we will be continuing with further discussion regarding few more illustrative cases of projections of the oblique solids in the coming lectures over here. So thank you very much. Thanks a lot.